Hello everyone, myself Ankur. I am a postdoctoral research fellow in University of Johannesburg. So today I'm going to talk about the impact of magnetar on the kilonova afterglow emission through the very late time radio observation. So GRBs, we know it is the brightest electromagnetic explosion in the universe that can outshine all the other objects in the gamma ray bands for a particular time. But the central engine of the cataclysmic event is still like debatable, and there are some indirect evidences for getting the central engine, and I am actually going to present one of the methods. So this is the basic and the preliminary classification scheme for the GRBs on the duration and the progenitor based scheme. So it is actually classified as long soft and the short hard burst. Depending on the duration, you can see there are different objects. So short GRBs has the lesser time span, and the long GRBs has like more than the short ones. And long and short GRBs both have distinct progenitor population and also the different host galaxies. So long GRBs are basically coming from the collapse of a massive star, which is confirmed by the supernova connection, and the short GRBs are connected with the gravitational waves. So, and also it came from the binary neutron star merger with the coincident detection of the GRB 170817 and GW 170817. It is finally confirmed that now. Yeah, so these are actually the aftermath of the binary neutron star mergers. The same scenario can happen for the neutron star and the black hole merger scenario. Yesterday in talk, they have actually mentioned about the different phases of the binary neutron star merger. The first phase is the inspiral phase, where the momentum and energy is loosened by the gravitational wave radiation. The second phase is the merger phase. Third is the accretion phase, and finally the ring down phase. Depending on the final binary mass and the equation of state of the neutron star, there can be four different scenarios that is possible. So if the binary neutron star mass is less than 3 solar mass, so in between the merger and the black hole formation, there is a transient state which is known as the hypermassive neutron star or a magnetar. So like, what are the signatures of the magnetar? So it actually can sustain the radiation for a certain time. So you can see the X-ray plateau in the swift XRD light curves. And that's why we have selected only those short GRBs showing this kind of signatures in their X-ray light curves. And also because we are actually dealing with the kilonova afterglow emission, we have chosen the samples for which the kilonova has been already detected. So now coming to the kilonova afterglow emission, I'll actually describe a little bit. So there are two different energy injection channels from the GRBs. So from the central engine of the GRB. So one is through the normal jet afterglow emission, and the second is through the kilonova afterglow emission. The kilonova is nothing but after the neutron star merger, the environment is highly neutron rich, and the rapid neutron capture process is going on. So all the higher order elements which are present, so they actually can go to the actinides or lanthanide series, and they go through the beta decay process. And this emission is known as the kilonova emission. So if we actually consider the central engine is not a black hole, it's a millisecond magnetar. So it has the tendency to release the energy via spin down process. And this energy will directly transfer to this mildly relativistic ejecta. And when this mildly relativistic ejecta interacts with the circumstellar medium, it produces the synchrotron emission. So that is known as the kilonova afterglow emission. So here the necessary parameters actually we have actually for the search. So the first parameter is the time of the observation. So the time of the observation depends on the rotational energy of the magnetar and the number density and the initial velocity of the ejecta. So depending on their permissible limit, it can actually vary from 2 to 10 years since the burst. So that is the time span actually we have chosen. The second thing is the observable frequency. If we actually see the spectrum, it peaks around the very low frequency radio regime, around 600 megahertz. So that's why we have chosen GMRT for our observation. So before our study, there are 3-4 studies has been already carried out using VLA and ATCA, but that is in the higher frequency ranges. So this is the first ever study of the kilonova afterglow emission using the GMRT. Now, in the sample selection, we actually discarded all the samples from the previous studies. As the signal expected is very weak, so that's why we have chosen the redshift up to 0.5. We discarded the samples having low number density from the afterglow modeling, because then the shock might be very weak. Then no potential signature. I have already mentioned about the X-ray signatures. So this is the early time X-ray axis, mid time X-ray plateau, or the late time X-ray axis. So we actually selected only those GRBs showing this kind of signatures, and also the kilonova signatures in the optical and IR light curves. And finally, you can in some of the bursts, you can see this kind of signature is present in Rawlinson et al. 2013. They presented some of the bursts having this kind of signatures present in their light curves. And finally, the burst having southern declinations beyond minus 30 degrees. So we have discarded due to the inaccessibility of the GMRT. Now, after putting all the selection criteria, we have 5 bursts, and that is observed with GMRT in band 3, band 4, and band 5. The observation time scale spanning from 2 years to 11 years since the burst. But unfortunately, like the previous studies, we could not detect the late time kilonova afterglow emission, which leads to the stringent upper limit of the GMRT. Now the question is that what we can do with the upper limit. So we tried to actually model the emission to constrain the number density as well as the maximum energy possible from the magnetar. So the first, we have considered a spherically emerging ejecta, which has the initial velocity of beta 0, and it is emerging from the central engine. Now, if it is influenced by the magnetar, then the kinetic energy can be calculated. And because it is starting from the relativistic regime to the non-relativistic regime, so the transition from the relativistic to non-relativistic one is also necessary. So that's why we considered the evolution of the bulk Lorentz factor of the ejecta. And then as it is expanding spherically, so considering the spherical geometry, we calculate the deceleration radius as well as the deceleration time. Finally, the peak flux of the synchrotron and the peak frequency of the synchrotron emission can be calculated from the Debicki-Lightman. So here you can see this is the model light curve of the model, and there are 4 different parameters which are very important. The first thing is the energy injection from the central engine. Second is the number density, ejecta mass, and also the observation frequencies. The other things like the microphysical parameters, epsilon E, epsilon B, and the power law index P. So that is actually kept constant because we don't have the detection. So that's why we need to actually reduce the number of parameters for the simplicity. So here you can see the peak is coming, peak of the light curve is coming. There can be 2 different reasons. So first can be because of the deceleration, and the second can be because of the optically thick to optically thin transition. But we are actually dealing with much later time from the central engine. So that's why we expect that the ejecta is optically thin. So this peak of the light curve is coming because of the deceleration. Now, this is the model light curve for GRB 05, 07, 09. This is one of the sample GRBs we have taken. We considered 2 different energy scenarios, 5 into 10 to the power 51 arc and 10 to the power 52 arc. So from the upper limit, we can actually constrain the number density stringently. That comes around 10 to the power minus 4 to 10 to the power minus 3 centimeter to the power minus 3. So from that, you can actually say that this short GRB actually happened in a very low dense ambient medium. Now, another thing we can constrain is the allowed maximum rotational energy, which is transferred to the ejecta. So here you check the deceleration time and the flux equation, which is dependent on the rotational energy and the number density. So there are permissible range for the energy and also the number density. If we actually calculate it, we will get multiple values of the peak flux. So if the model flux at deceleration time is less than a 3 sigma upper limit, then we call it the allowed space, and the model flux is greater than 3 sigma upper limit, we call it a forbidden space. So here our purpose is to actually create the energy versus number density parameter space plot. So here you can see this field space is the allowed space, and the white space is nothing but the forbidden space. And the maximum energy theoretically possible for a magnetar is around 10 to the power 53 hour if you actually choose the Stief equation of state. And the vertical column is the number density constraint. In the table, you can see the number density column, which is constrained from the afterglow modeling. For 061210 is the only one GRB for which the number density constraint was not available in the literature. So that's why we cannot actually put the exact value of maximum rotational energy for the magnetar. Now, these are the other three scenarios. So in this case, the 05, 07, 09 is the minimum energetic scenario from our sample, and 14, 09, 038 is the highest energetic scenario possible. So if we actually consider the less Stief equation of state and the maximum rotational energy is around 10 to the power 52 hour, then also the 05, 07, 09 and 10, 06, 25A can be discarded from the magnetar sample. So for those two GRBs, actually we can say after the merger, it directly prompted to the black hole. There is no magnetar present in those two GRBs. But for 140903, it is the most probable scenario for which the magnetar can be present. Now, this is like I have already summarized all the results. Now, for the future prospects, we have already proposed in MIRCAT because this sample is up to 2017. So after 2017, there are so many short GRBs happened. So we proposed in MIRCAT to find the late time kilonova afterglow emission because MIRCAT has the better sensitivity than the GMRT in the low frequency radio regime. So we can expect that there will be some detection. If it is detected, then it might be the first ever detection from the late time kilonova afterglow. In GRB 170817, there is some X-ray excess from the kilonova afterglow, which is reported by Hazela et al. So we can expect that there will be some radio excess in the later time, but still 170817 is in the quiescent phase from the last VLA observations. So maybe in the later cycle, we can propose for 170817, but this time we are not restricting our sample to the short GRBs. We are also considering the long GRBs with the kilonova connection and also deep kilonova limits. So even with the future generation telescope like the SK, which will have the much better sensitivity than the current generation, so we can detect this kind of very faint emission in future. So yeah, thank you for your attention and please go and check out my paper.